Sometimes they're on a really good sale.
Good morning, everybody. How we doing? Last 2 weeks of school? Yeah, it's all coming to a head, isn't it? Let's see here. I will tomorrow start giving instructions about how to turn in quiz sheets and stuff like that. I know some of you are going on a biology field trip. Don't worry, right? You got till next week to turn stuff in. And then what we're going to do today is I'm going to do a couple of things that are kind of best done sort of in this room as opposed to the lecture room, which includes, so I'm going to teach you about, I'm jumping ahead a little bit in the lecture. We left off last time talking about the different kinds of radioactivity, but we're going to jump ahead to half-life and what it is and how we measure it. We're going to do a half-life simulation. So this is kind of like our lab exercise for today. And then I'm going to expose you to some radioactive materials and get you nice and glowing before you leave lab. No, not that much. But anyway, let's begin and let's talk about Half-Life. Quite possibly the best video game franchise of all time. And I'm half serious. I'm not going to talk about the video game right now, but if you have not played Half-Life, you need to go play Half-Life. It defined the modern first-person shooter, and the protagonist, the hero in the video game, PhD in physics, carries a crowbar. Okay, so let's talk about what Half-Life really is. And the way we're going to do this, okay, is we are going to simulate a radioactive substance. Half-life is a statistical measure of something that is inherently random. A nucleus will do alpha, beta, or gamma decay with a random chance. And those probabilities are dictated by laws of physics that we'll get into tomorrow. But at its core, alpha, beta, and gamma rays happen at random. What we're trying to do is capture something that can be measured with predictability out of random chaos. And to help us understand what that's all about, I am going to turn you into a sample of radioactive material. Let's see here. I need 23 volunteers. Okay? And I need to know so we need calculators out because we got to do some basic arithmetic and that's always dangerous. I need to know what 23 times 5 is. 115? You guys are quick. Okay. What I've got here, okay, are some baskets that have 6-sided dice in them, okay? I need everybody to take 5 of these dice, okay? And it's important that you get the right colors, of course, right? So you know, I'll leave that up to you, okay? But let's do this and this. Make sure that I only have 6 containers, so make sure you spread them out. Tables that didn't get them, get some dice. So get 6 of your favorite, or 5 of your favorite die. And then everybody needs 5 pieces of paper. Oh my gosh. That's already happened. We're dropping the dice on the floor. I'm sorry. Oh yeah, why do I have all these? That's not the question. How did I get there? That's the question. Amazon.com, pound o' dice. They sell them by the pound. Okay. So, yeah, but we bought 2 pounds of 6-sided dice from Amazon. I think a pound of dice runs you about $20. Yeah, it's a bunch of random 6-sided die in a bag. I think a lot of them are like, there's problems on the die, right? There's misprints or whatever. And you can get a set with a pound of all these together. All right. What have I given you? Okay, stop rolling. Oh gosh. You're gonna have plenty of time to roll these, don't worry. So by the power invested in me by the state of California and the fact that I control all of your futures, I now make you radioactive. Each one of you, I know it feels great, doesn't it? Make sure dice and paper get to come on there. So what I've done is I've made you not 1, not 2, but I have made each and every single one of you 5 nuclei. Okay? So each one of your dice represents a nucleus that can decay with a probability. And if we set a rule, and the rule is, if you roll a 1 on one of your dice, that nucleus will decay. So what's the probability, if it's a 6-sided dice, what's the probability that a decay is going to happen? It's 1 in 6, right? So you are going to be rolling and representing 5 different nuclei, right? You're going to, don't do it yet, but you're going to roll dice, and if you see a 1 pop up, it means that that nucleus has decayed, okay? Meaning that it's emitted an alpha, beta, or gamma particle. You're going to remove that die from the pool. You won't be rolling it again. You will take and eject a particle from that nucleus. Your particle is going to be one of these pieces of paper. Everybody has 5 pieces of paper? Crunch those pieces of paper up into little tiny balls. You need 5 pieces of paper, all crunched up, and have 5 different wads of paper, 5 different round balls of paper. If one of your dice decays, rolls a 1, you're going to set it aside and not roll it again. You're going to pick up one of the pieces of paper and you're going to throw it towards the front of the room. That's the radioactive particle you are ejecting. Okay? I am going to be the Geiger counter. I am going to count the pieces of paper as they fly towards the room, front of the room, okay? So please, try to throw not when your neighbors are throwing, right? I don't want to see all these particles coming at the same time. It's hard. This counter has a rate limit, okay? I want to be able to count them accurately. So like try to stagger your throws. If 2 or 3 of your dice rolled 1s, you got to throw 3, throw them one after the other, right? If somebody next to you is throwing, just pause for half a second and then throw yours, right? So I can try to count them. There are some rules, okay, about this. Very important rules. First rule is, if you hit me, you get an F. Okay? Second rule, if you're sitting towards the front of the room, duck. Third rule, if you hit me, you get an F. Right? We understand the rules? Okay? All right. So everybody should have 5 pieces of paper and 5 dice. I think we had 2 people. Did I say 23 times 5? So it's now 25 times, that's 125, right? Okay. 25 times 5 is 125. Okay, so what are we going to do up here? What we're going to do is we are going to graph. We're going to keep track of our data in visual format. Okay, along the x-axis, time will be going by. There will be individual time periods, not measured like in seconds or minutes or hours. We're going to measure this in Balogh, units of time called Balogh. That's along the x-axis. On the y-axis, we're going to count the number of, we're going to keep track of the number of nuclei remaining, right? So ones that haven't decayed. We're starting with 125, right? So 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 10, 20, 30, right? 10, 20, 30, 40, 80. I promised myself over the years I would always get some graph paper for this, but I never seem to be able to do it. Okay, so we start with 125, okay? And so this axis right here is number remaining. Okay, that's supposed to be an N. It didn't come out quite right. Okay, number remaining. Starting with 125 of these nuclei. Okay, to be clear, right? You represent 5. You're rolling for 5, okay? So what I want you to do right now is pick up all of your dice, right? Shake them up, getting nice and random, okay? Roll them. If it's a 1, move the die aside and throw paper. Did you pick up one and rethrow it?
Is that allowed?
No. So 21. You can throw it if you want, but like the one landed in front of you and you threw it.
Yeah.
Okay, so 21. Okay, there were 20. So what's 125 minus 21? 104, right? Okay, so that means we have 104, which would be somewhere around like right in. Come on, right in there. Okay, so we have 104. We lost 21. Okay, do it again. So again, you're not. If it's a 1, you're not rolling that one anymore, right? You're picking up your remaining, rolling.
I lost the tiny die. No risk, no reward.
I counted 15 that time, and Toby is running really close. What's 104 minus 15?
89.
89, thank you. 89-ish, right about there. So that's kind of interesting. The first time we rolled, we had 21 decays. But now we have sort of less die, right? And then it was 15. So that kind of tracks a little bit. We'd expect that to happen. Okay, roll again. Okay, interesting. 15 again. Even though we had less to start with, we ended up with the same difference. What's 89 minus 15? 74. 74-ish on our graph here. Okay, do it again. Just roll once. Wait, nobody decayed? Really? That hasn't happened in a long time. Like more than a decade. Okay, this is really, really good, right? Notice what determines whether or not a nucleus is going to decay. A roll of the dice, chance. It's random. Could there be a time period when there's no decays? We just had it. Like first time seriously, I think in like 17 years. Okay? This is a big moment. I think we should have a moment of silence. Okay, that's enough. All right, so nothing happened that round, right? We were -0. We're still at 74, which is going to make our graph look really weird. Okay? That's all right. Now, how many of you have only 1 die left? Anybody? I may only have 2 left. Ah, interesting. Okay. Does anybody have 5 left still? Christian, okay. How many of you have 4 left? Do you see how we're kind of all over the place? Some people are almost run out, and other people still have 5 or 4 left, right? It's totally random. All right, pick them up and roll one more time. Go once, right, and then throw.
Did it? Like how did it?
You okay, Valerie?
Yeah.
Okay.
It's okay.
Robin wasn't aiming for it. It curved, I thought.
It curved.
Okay, I counted 12 that time. 62? No.
Yeah.
Yes. Why not? Okay. All right, do it again. Nine. 52 is 53. Right? Cool. Okay, again. People are getting really nervous now. What's 64 minus 8? 46? Ish. Okay, again.
Got it.
Just this side of the room? I counted 6. I've been not keeping track here. 40? Okay, so how many of you are completely done? Just how many of you only have 1 left? Okay, that's a lot of people. Anybody with 4 left? 4 more? No? 3? Okay, so we're down kind of low. Okay, so what I want you to do is because how long would it take for everybody to get done rolling their dice? Long time. We could be sitting here watching one person roll over and over, right? Okay. So what I want you to do, pick up all your remaining dice, okay? And when I tell you to, I want you to roll. So you need to remember 2 things. You need to remember how many you started with, right? So if you started with 3, started with 2, or started with 1 die, right? I want you to roll, remove ones, and roll, and just keep rolling, removing ones that pop up as well, and just count the number of times it takes you to roll to get rid of all of your dice. Does that make sense? Okay? So I want you to roll and get rid, roll and get rid, and just count what, I need to know what you started with and how many times it took you to get rid of it. And then if you feel like you want to throw paper, go ahead and throw paper. Go.
No, I realized after.
What's going on over there, please?
Huh?
What's going on over there? Students in the other lab are doing something. We still have people rolling out there? Alright, now, hold on a second. How many did you start with?
2.
You started with 2. What roll are you on right now?
11.
11. Okay, can anybody beat 11? Anybody rolled more than 11?
You were done.
I started with 5 because I was already finished and I got 7.
That doesn't count. Jordan, you had 2, I think, that you started with? Did it happen the first time you rolled? Yeah, okay. So I was watching Jordan out of the corner of my eye, watched two pieces of paper go by, right? So Jordan with 2, you only needed 1 roll for both of them to come up snake eyes, right? You had 2 and needed 11, right? More people were continuing rolling out there, right? So it's entirely random, isn't it? It could go out quick, or it could just be this thing that takes a long time. So if we look at this data, right, it doesn't seem like there's kind of anything of a pattern to pull out, except for the fact that it is decaying, right? There is this steady drop off in the number that are remaining. So we take some math and we do something called a curve fit. We look at the data, we try to fit. This is not a line, okay? It's not a straight line. Straight line's not gonna work here. Instead, what we do is we mathematically fit the data and push it out like that. This turns out to be an exponential curve. If we ask the computer to fit this data and it comes back with a function, the function is going to look like this. The number we have is equal to the number we start with times the e to the minus lambda t. Where lambda is not the wavelength, sorry, it's a decay constant. It's a number that sets kind of how steep or shallow this curve is. From this, we can pull predictive information, right? We can kind of plug in any time t. If we know lambda, if we know the decay constant, we can plug in a time and then predict kind of where we're going to be on this curve. The half-life is defined as the time that we had half of our starting amount remaining. We started with 125. What's half of 125? 62 and a half? Is that right?
Yeah.
Okay. So somewhere around 60, this is about our halfway point in our population that we started with. We draw a horizontal line over until we hit our curve. And then we go straight down and we see here that the half-life for polonium, 4, it looks like it's about 4.9 Balogh. 4.9 units of time, which we defined as just a roll of the die, right? Okay, is how long it took for this radioactive sample of polonium to lose half of the amount that it started with. If we let another half-life elapse, first of all, how long is that half-life going to be? 4.9, okay? Meaning it's going to be 8, okay? So let's see here. We would take half of what we start with. We start with 62.5, so about 31-ish. So somewhere right here, oops, do it in red. So we take, we go, we hit the curve. Okay, I didn't quite get there, right? It should have been 8.8, but my curve is a little bit funky. Forgive me, I'm not using a computer, I'm using my eyeballs, right? Okay, but about another half-life went by. Every time we go through a half-life, we take half of what remains. So after 2 half-lives, how much remains compared to the very beginning? If we start with 1 or 100, how much do we have left after 1 half-life? Half. And then after 2 half-lives?
A quarter.
A quarter. It's a half of a half, right? And then after the 3rd half-life? An eighth. A half of a 4th is an eighth. And after the next half-life, a 16th, a 32nd, a 64th. You get the idea? Okay? Every half-life that goes by, half of what remains decays. It is a statistically determined value, a singular value that can give us information about what's going on, even though it was drawn from random chance. This is what it means to measure the half-life of a material. This is also what it means for the material to be radioactive. We're going to repeat this experiment. Before we do that, I need you to come up here and pick up 5 pieces of paper. They're all over the place. You don't have to find the 5 you threw. Just get any 5. Everybody needs 5. If we lose some, I've got some extra.
5.
If you guys here, I have a bunch.
Anybody need some? These are extras. You guys need some? Got 5? Everybody's back to 5? Okay. Radioactivity is a measure of how many decays are happening in a time period. So half-life actually is an indirect measure of this. We're going to go over the units more tomorrow when we're in lecture. But a singular event, a singular decay, a singular radioactive particle coming out of the nucleus is referred to as a becquerel. So a becquerel is a decay per second. The actual measure of activity is a unit called the curie. You kind of have to wonder where we came up with these names, right? Okay, so becquerels, right? It's rare to have just 1 decay per second coming out of something. Usually there's trillions upon trillions of them happening, and so the curie redefines. It's like, I don't know if it's like a trillion or 10 to the 15 becquerels per second or something like that. If a radioactive sample has an activity that's around a curie, you don't want to be anywhere near it. That's a highly radioactive thing. It's giving off lots of radiation per time. But I want to do something here to underscore the relationship between radioactivity and half-life. What we're going to do is we're going to change the odds. We're going to do exactly the same simulation or experiment again, only this time, anytime your dice rolls a 1, 2, or a 3, you're going to remove it from the pool and you're going to throw the paper. So what's the probability now? It's like 50-50, right? We were 1 in 6 before, now we're 1 in 2. That there's going to be a decay that takes place. What is your prediction for the radioactivity, the number of emitted particles per time period? Is it going to go up or going to go down? Probably up, right? Because we have just a lot more chance for there to be a decay, right? So let's see and what do you think is going to happen to the half-life? Is the half-life going to be a bigger number or a smaller number? Bigger number? Bigger half-life, more radioactive? Smaller half-life, more radioactive? All right, let's see what happens. Okay, so pick up your dice, roll them, 1, 2, or 3s, get paper strong. Was that all? Oh, we got it. That it? Felicity, how many do you have left?
None.
Anybody else lose all of theirs? Does anybody have 5 remaining dice? Okay, totally random, right? Like totally random. And if you think I actually counted all those, you're pretty funny. but I know what the curve is supposed to look like, so trust me on this one. When I first was teaching this, it was back when Al Gore lost to George W. Bush. My students demanded a recount. All right, go again. I counted 36. So I made this just a little too steep. This should be like more up here and then like down here. Okay, do again. One hit me
Oh,
on the bounce. I counted 16. So I think we can see kind of what this curve is doing here, right? Okay, so there were a lot more pieces of paper per time, weren't there? And if we come up here and we draw a curve, it'll do something like this, okay? And when it comes to the half-life of this sample, again, we start at the halfway point, come down, hit the curve. Is the half-life more or less than it was before? It's a whole lot less. It's like half a Balogh, isn't it? Okay? But it was more radioactive. The shorter the half-life, the more radioactive the substance. So let's talk about that. I have the correctly laid out periodic table over here, right? And I've got uranium sitting right here, okay? Uranium, like the poster child for oogie boogie radioactive stuff, right? Make bombs out of uranium, all that kind of stuff. So uranium 238, 235, both of them, has a half-life of 4.5 billion years. That's billion with a B, okay? More on that later. Iodine. I forgot to look up the isotope again. I think it's 127. Iodine 127, or it's 117. I can never remember. It's got a 7 in it somewhere. Okay? Has a half-life that's measured in hours. Uranium make bombs. Iodine 127 injected into patients that are going under X-ray machines to get a hyper-accurate picture of what the blood flow might be in their brains or their arms or their stomachs or whatever, so that we no longer have to cut you open to let the demons out. Talking about a radioactive tracer that's used in medical imaging. Which of those two things is more radioactive? Uranium with its 4.5 billion year half-life, or iodine with its hours, it's like 22-hour half-life. Iodine, by a long shot, right? It takes uranium 4.5 billion years for half of it to decay. That's not much going on. Iodine will lose half of itself in about 20 hours. That's a lot going on. So why is it safe, for a given definition of safe, to be injecting radioactive iodine into patients, but it's not safe to be putting uranium on your salad?
Kind of radiation.
Well, iodine turns out to be I think it's a gamma emitter. In the medical field, it's deemed less risky to expose a patient to that level of radiation and get good diagnostic information than it is to have to cut open their brain to see what's going on, right? You balance the risk of those things, okay? Uranium, with its really long half-life, is always sort of, the poster child of all evil in the universe or whatever when it comes to radioactivity, but in fact it's not that radioactive, and uranium's radiation isn't actually the primary problem. I worked with this stuff in graduate school. Kind of explains a lot, doesn't it? And we were I mean those of us that were using it and those of us who were in charge of us using it, were more concerned with the chemical properties of uranium than we were actually concerned with the radiation properties of uranium. Because uranium will give you the equivalent of lead poisoning with like 100,000 times smaller exposure. Like just a few inhales of uranium dust, your liver starts dissolving, right? So it was the chemical properties of the material that was worse than the radioactive properties of the material. So we will talk more tomorrow about radiation safety and how to know when you're safe and how to measure and all that kind of stuff. What I wanted you to see was the fact that the correlation between half-life and radioactivity is probably opposite what you may have thought before coming in today. The shorter the half-life, the more radioactive. But that doesn't necessarily tell you how dangerous, right, the radiation exposure is. And we'll get more into that tomorrow. How do we use this, though, in the context of problem solving, and where would we use it, and how can we use it to figure things out? Well, this is the example I want to do, because one of the powerful things we can do with half-life is if we can compare a known amount, let me back up for just a second. I forgot to mention something. This equation I've written up here is actually not very useful. It's true, it's a mathematical fit of what's going on, but it's really hard to count numbers of radioactive nuclei. Like you really can't go in with a pair of atomic tweezers and like start picking out all the uranium bits, right? Okay. So what's better is to do this in terms of something called rate. The number of decays per time that are taking place. This is the actual functional one that we can apply. A rate, okay, again, is a decay per time. And that time value can change, right? It can be seconds, minutes, hours, years, whatever. Okay? So it's the rate version that we will use instead of the actual. You divide both sides by time and you get the rates. All right, so we could, in theory and in practice, if we knew what a starting amount of a radioactive isotope is versus what we measure the rate to be now, assuming that something happened that caused the amount of radioactive isotope to no longer be ingested by something, we could figure out how much time had gone by, right? We start with a known rate, we end with a known rate, we can figure out how much time has gone by for it to decay to that point. This is the essence of radiometric dating, and we're going to use the example of carbon dating to do this. A lot of biologists in the room have taken anatomy and physiology. What do the lungs do? What's their primary function?
Breathing.
Breathing. And what is breathing?
Inhaling.
Okay, inhale, exhale. But what do your lungs do with the gases that are put into them?
Go to your blood.
Put it in your bloodstream, right? That's the lungs' job. Whatever you breathed in, it's going into your bloodstream, okay? Right? So, as an organism, you are exchanging air, material with your environment constantly. You're ingesting food, you're breathing air, and with every breath, you are topping off the amount of carbon-14 that exists inside of you, okay? And some of it will decay, it's always decaying. Carbon-14 has a half-life of 5,730 years. And every breath, you're topping that level up. Anything that's decayed gets replaced, and we maintain a certain amount of carbon-14 in us at all times. And then the organism dies. And what's one of the side effects of death? Stop breathing, right? Stop exchanging materials with the environment. In fact, you become the environment. And the parts of you or the organism that are left behind usually are like the hard parts, which would be bones, teeth, I have a friend that's convinced that modern or future archaeologists are just going to be unburying humans, and we're going to be nothing but 2 kidneys sitting there because of all the microplastics and everything else we put into our bodies, right? So anyway, organism dies, right? Stops exchanging carbon-14 with the environment, amount of carbon-14 in the hard tissues begins to decay. And that's what we've got. Not right here. What happened? Oh, thing keeps wanting to update. So we have a sample of carbon-14, right? We've taken a 50-gram sample of bone, and we measure a current day rate of decay of 200 decays per minute. However, according to this problem, the amount of carbon-14 in stuff that's like alive is 15 decays per minute per gram. I don't know why that sentence ends the way it does. I have no idea what happened to my slide. Okay? And they want us to find the age. So, okay. So there's a bit of an issue here. Like, if this sample is, okay, so carbon dating can date the age of death of something going back about 70,000 years. After 70,000 years, we just get a lot of error, okay? A lot of half-lives have gone by, and it's really hard to get measurements. But it's also kind of hard to use for anything that's less than 2,000 years old. Again, not enough half-life, not enough decays have happened to kind of distinguish it very well from the regular background amount of carbon-14. But we also know that carbon in the atmosphere has changed in its concentration over history. Like, it's just, we humans are putting more carbon into the atmosphere now, so we know concentrations are really high right now. But in the past, it's fluctuated up and down. It's not a constant thing. So what we need to know is, we need to know kind of at the point where this thing died, whatever that was in history, we need to know what the background amount of carbon-14 would have been at the time. We need a time machine. Luckily, we have one. It's called Greenland. Or Antarctica, depending on where you want to go. What do Greenland and Antarctica have in common?
Opposite poles.
Well, that's not a common, that's opposite. Greenland's losing a lot of it. It's all melting.
Ice.
Ice! All right, okay. Yeah, Greenland is named wrong. Iceland is green and Greenland is ice. Anyway, it was a cartography mistake. The point I'm trying to make here is we have a time machine, and it's in our ice caps. Scientists have drilled into the ice and pulled out these ice cores where you can literally see the layers year by year of snow that was deposited and then compressed by the snow that came the next year, and the next year, and the next year, I'm assuming mixed in with some polar bear pee or whatever, right? Okay? So you've got these layers going back. You start at the top, you start counting down, you're going backwards in time. We are talking kilometers worth of ice, miles deep ice sheets. And there are ice cores that go back 400,000 years. And in those layers, trapped between the snowflakes, are little bubbles and pockets of gas. The atmosphere as it was when that snow fell. You get a little tiny needle, you get in there and you very carefully extract that gas, measure the concentration of atmospheric carbon, and you know what the rate was going back through time with almost yearly resolution. It's an incredible library. And I believe there are 3 libraries that are maintained on the surface of planet Earth for the sole purpose of keeping these ice cores cold. Libraries, they're big warehouses built underground that are kept at like -30 Fahrenheit all the time to make sure that the ice cores don't melt and can be studied whenever they need to be. So, we know how to find what the atmospheric carbon rate was going back hundreds of thousands of years. we have a sample of bone where we measure the decay rate in that bone today, and we're going to make a calculation that gets us back to how long ago this thing stopped breathing, right? Stopped exchanging material with its environment. So we have this rate equation, and we've got to extract time from it. We've got to solve this equation for time. Luckily, we only need to do this once, and so if you have no memory of how logarithms work, then you're okay. Just hang on for the ride and use the thing I box at the end, okay? But we need to get t out of that exponential. Does anybody remember how to get t's out of anything out of exponentials? It's the natural log. Remember any of that? Okay, so I'm going to isolate all the constants on one side and get my exponential on the other. Woo. And then it'll be about 5 minutes. You're welcome to sit and watch, but just letting you know. And then if I take the natural log of both sides of this thing, I'll end up with the natural log of this ratio of rates, and then the natural log of e to the something is the something. So this is negative lambda t. I can divide by the negative lambda, like that, and I've got the time that would have elapsed. So given a known rate now and a known rate that it should have been when it expired, I can find the time, assuming I know this decay constant. Well, the decay constant, the half-life, mathematically turns out to be the natural log of 2 divided by that constant. And so we can go find that constant if we know the half-life and then be able to plug it in. So let's find our decay constant first, and then we'll come over here and find out how much time went by. We know the half-life is 5,730 years. We have the natural log of 2 lambda, so we divide natural log of 2 by 5,730. I forgot to bring my notes today. Calculators. What's the natural log of 2 divided by 5,730? And get it shouted out, and then when somebody else gets it, shout out. We'll see if you agree.
I got 1.2 times 10 to the negative 4.
1.2 times 10 to the minus 4. Same thing. Let's go a couple more digits in there. 1.2, probably 0.
09.
0.9. Okay, we'll stop there. Times 10 to the minus 4. And the units, what do our units end up being? It's an inverse here. Do you see how the years is down in the, okay, so it's like 1 over years, which is awkward. Okay, but we got that constant. Let's step over here. We got these rates, right? So what's the rate now? What's the problem say? Does it say 200 decays per minute? Right, we extracted this sample of bone and it says 200 decays per minute. So my rate now, 200 decays per minute. And what should it be? Like when it originally started, what does the problem tell us? What's the number?
15.
It's weird. It's 15 decays per minute per gram. All right. These two rates are not being expressed in the same units. One's a decay per minute, one's a decay per minute per gram. So we need to fix this. The bottom line here is it actually doesn't matter what the units are as long as they are the same. Because we're going to stick them in here and we're going to form a ratio. If we have unit on top and same unit on bottom, what happens to all those units? They cancel each other out. So the important thing is to get them into the same units. Doesn't matter what the actual time is. Years, eons, whatever, okay? Decays, curies, whatever, right? It doesn't matter as long as they are the same, right? So, how do we get them to be the same? There's one number we haven't used yet. The 50 grams, right? So, I could either take my 15 decays per minute per gram and multiply by 50 to get rid of the grams and end up with the rate that it should be if I had 50 grams of the material, right? Or I can take 200 decays per minute and divide by 50 grams to get decays per minute per gram. It doesn't matter which way you do it, I can divide 200 by 50 easier than I can multiply 15 times 50, right? So I'm just gonna take my 200 decays per minute, divide by my 50 grams, and then that makes my R equal to 4 decays per minute per gram. And now I look at that and I go, wait a second, okay, does that make sense? Should I have less now than I started with? What did we learn from our half-life curve? We start with more, and as time goes by, we end with less. All right, so now I can come over here and find the time. Negative sign's making me nervous, but let's see what happens. 4 over 15. Again, I made the units the same, so I'm gonna put the units in because they're all gonna cancel anyway. All over 1.209 times 10 to the minus 4 inverse years. Oh boy. Okay. What kind of number is the natural log of 4 over 15? Doing your calculators, what do you get out? It's a negative number, isn't it? Because when you take the natural log of a number less than 1, you get a negative number. So this will always be a negative number, because we always have less now than what we started with. That negative sign will cancel, and the time will become positive. Yay, right? And then we can divide by whatever our decay constant is, and we should get a number that's like 10,900 and something?
26.
10,926? I remember that from last period. 10,926 what? We have a 1 over a year. So what's the moral of the story here? The units of your rates don't matter as long as they're the same, right? The problems will try to trick you. Just make sure your units end up being the same. The units of your decay constant, you don't need to convert to seconds, right? Or minute, whatever, right? If they give you a half-life in minutes, you can keep it in minutes because it's the only unit that's going to survive through all this. And so if your decay constant's in minutes, what is your answer going to be in? Minutes, right? Decay constants in years, so on and so forth, seconds, whatever, right? You don't have to go back to the standard units of seconds here. You don't have to go to standard SIUs. Just make sure the units agree between the rates and then obey the unit you have on your half-life to get the decay constant, and you'll be good to go. All right. The other moral of the story is we can't, with precision, say that this is 10,926 years. Okay? There are error bars on the measurements of these rates. If somebody came to me and said this thing was about 11,000 years old, I'd be okay. If they came to me and said that this thing died on the second Wednesday of April 10,926 years ago, I'd go, you're smoking something. Because we can't be that accurate with something, right, that has these measurement errors in it. I'm not saying it's inaccurate beyond more than 70,000 years and earlier than about 2,000 years, right? There's a window of opportunity for carbon dating. So when they go and dig up rocks in Australia, then they say that some of them are like 3.7 billion years old. How do the geologists know that? Can they use carbon dating to figure that out? No way. They're using potassium dating. Potassium-40, naturally occurring after the decay of radon gas, has a half-life of about 4.7 billion years. The Earth has been around for about 4.5 billion years. So we have about half of our potassium-40 remaining that we started with. Okay? And that isotope allows us to date things better. But geologists are also like, yeah, it's 3.7 plus or minus 100 million years, right? For them, 100 million years is nothing. All right. That's enough on half-lives and radiometric dating and all that kind of stuff. Dr. Kerfoot is here to watch me. He's trying to figure out how to do this with his class, so we will do this demonstration now. So this is something that I want you to remember when we're going over tomorrow all the units of radiation and things like that. but the demonstration is actually easier to do in here than it is to do in lab, or at least more of you can be exposed to radiation this way, okay, than I can do in lab. I have with me, okay, and you'll notice that I did put my gloves on. I better button up my lab coat. Serious science is going to happen now. You have a lab coat?
Yeah.
Okay, you don't need it, you just need the gloves. All right, but the theater is very important. Okay. The gloves are actually very, very important from what's going to happen, but not for the reason that you think, okay? So I have here what's called a Rad Scout. This is it's a very souped up Geiger. It's not a Geiger counter, number one. Geiger counters very specifically measure the presence of ionized charged particles. This counter is a radiation detector, a scintillation counter, and it actually measures radiation in something called microsieverts per hour. So it's measuring a rate. It's a per time thing. I don't expect you to know what a sievert is yet. I haven't taught you about it. But right now, in the room, it's increasing. No, okay. It's about 0.18 microsieverts per hour. But you can't see the screen. Right? It's kind of, sitting there. So we've got to make this scarier. What's that? What are those beeps? What did the sensor do? What did it detect? It says right here, alpha, beta, or gamma. Every one of those audible clicks is a singular radioactive particle that this detector has detected through its window right here. And so what is this detector detecting right now? Radiation. Where is it coming from? Toby? No? No? Okay. Are you guys radioactive?
Yeah.
Yeah, mildly. Okay. Are the walls radioactive? Yes. The dirt? Yes. The air? Yes. Radiation is a natural thing. Okay? Things that are alive have carbon-14 and other things. You probably ate a banana today. It's got potassium in it, gives off positrons, it's radioactive. Your biology evolved in a radiation environment. As a matter of fact, when you're cut off from radiation, your body starts freaking out. Something's gone wrong, okay? So radiation, like water, is like you don't want too little of it, but you also don't want too much. And tomorrow, I'll give you some scales and some ways of quantifying that and knowing when you're safe. But the reason I wanted to show you this today is because of this box that I have brought, okay? Inside this box, I have a lot of goodies, okay? So we'll start with these goodies, okay? I don't know if you can see them from where you are. These are little plastic discs, okay? And so since you really can't see them from where you are, I will bring some to you. Let's see, you want to bring one? Okay. Red ones for you guys. Hand those around. Okay, here we get orange, right? Let people see those, hand them out. Don't lick them. No licking, okay? What these are NRC exempt radionucleotides, okay? The NRC, the National Radiation Council, is the government organization responsible with keeping track of radioactive materials in the United States of America. I dealt with them during my graduate work because we had uranium in our lab. These are NRC exempt. Exempt means what? They don't care. It's not covered by the law. I can have these without having to have a license and have my facility inspected and all that kind of stuff, okay? So, in other words, there's so little material here, and it poses such a little threat to national security and public health that they don't care that I have it. Okay, so let's see. Red one. Okay, and by the way, in all of these, you can probably, this one's got a really big black thing, but on some of them, they're all closed up, but there'll be a little tiny smudge or stain down it. That's the radioactive material, okay?
Bless you.
So, this is polonium-210, has a half-life of 138 days. Alpha emitter. Caution, radioactive material. Okay, so there's my alpha emitter. I'm going to put my it's basically kind of what it was doing around the room, wasn't it? What's going on here? These samples were about 15 years old when I arrived here 23 years ago. Okay? Half-life of 138 days. How much polonium-210 is left?
Basically.
None. This is so many half-lives have gone by in this red. So if you got a red one, you're lucky. No, it's not. No, it's not. I shouldn't say things like that. Okay. Green one, strontium-90. Half-life of 28.6 years. Oh, okay. Beta emitter. Caution, radioactive material. Okay. Right? No, Mr. Beta, I can't believe you gave me one of those. What are you doing? Push it away from me. Orange one. Cesium-137. Half-life of 30.2 years. Mr. Bailey, you lied to us. Like, you said that the shorter the half-life, the more radioactive, and the red one didn't go off, and this one. Ah! Okay. All of those were human-made, man-made, right? They were generated in a lab, artificially made to be radioactive, or isolated in some artificial, not natural process. This is also not the reason I'm wearing the gloves. That'll become apparent later. What is this? Good, it's a rock. You guys can take geology class now, okay? This is a rock. This rock happened to be picked up outside of a silver mine in the Sierra Nevada mountains. It contains a lot of granite. This rock came from nature. There's the artificial gamma emitter. There's the one that came from nature. What's my point? You're never going to go walking in the Sierra Nevadas again. Granite is the type of rock that has the highest naturally occurring concentration of uranium of any of the metamorphic rocks, okay? And so that means that when you go up to the Sierra Nevadas and you park your rear end on a nice soft piece of Sierra granite for your lunch, right, okay, you are irradiating your rear end. You are, right? Some of you have liked laying down on the rock. Well, you know, radiation coming from both directions. Okay? Now, here is the reason I am wearing the gloves. Up to this point, I would have had any of that on my salad. This, right here, okay, this sample is wrapped in lead foil. That's the reason I'm wearing the gloves. What happens if you get lead in you? Lead poisoning, liver dissolves. Told you uranium was worse in terms of the chemical. This is why I'm wearing the gloves. This is why you should wear the gloves, okay, when you do this tomorrow, okay? Inside of this plastic case is kind of a semi-greenish. Does it look a little bit green, right, okay? This is a sample of rock that was taken out of a uranium mine. We pegged the meter, okay? In terms of numbers, so 269 at its peak on this meter. Here's the gamma emitter. 27. How radioactive is nature? Very, right? Radioactivity is a function of our natural environment. Tomorrow, we are going to go over what constitutes safe exposure. What constitutes allowed exposure? What's a legal limit for the exposure that somebody working around radiation can have? And so we're going to be able to sort of calibrate our idea about what radiation is all about. Your takeaway from this demonstration, though, is it's natural. Don't go out in the sun without sunscreen, but enjoy the radiation you get. Like I said, if you don't get enough of it, your physiology freaks out. Your immune system actually goes berserk. If you get too much of it, your immune system goes berserk, right? So we want to maintain a delicate balance, and I'll show you how to do that tomorrow. If you want to stay and get help on your homework, I will be here. Otherwise, those of you that are going on the biology field trip, have a fantastic time tomorrow. And for the rest of us, we will discuss safe radiation exposure tomorrow. Yes, I need all the radioactive samples and the dice. Thank you for those of you that organized all the dice, right? But I need the radioactive samples up here. Bring the dice up here and you got all that. And if several of you could please help pick up the radioactive particles on the ground and put them in the box, that would be fantastic. Thank you.